So in this question, we're going to look at an old classic type of carnival festival type ride that's been around for a long time, where you sort of sit in a chair and a thing spins around and you sort of go around and we get whipped around in a circle. And it's great little circular motion type situation. Lots of carnival rides and festival rides use circular motion like roller coasters, and there's so many spinning rides. It's unbelievable. And this is a simple little one here. So we got these guys moving around, and when they start moving around, they end up making an angle of 35 degrees with the vertical, and the path radius is 4.2, and we're going to find the frequency of revolution. Now notice there is no mention of the mass of the people, because the mass actually doesn't matter. And if you've ever been in a ride like this, you'll notice it doesn't matter how big or small the person is, you're all sort of in the same position, and by doing a little simple calculation here, we can sort of see why. So let's sort of map things out a little bit. And I'm going to sort of take it as though, maybe we have somebody out here or something like that. Maybe that person right there. If we sort of map out what's going on, they are sort of out to the side here. So, here's the person. We'll just draw them here, like something like that. You get the person out on the side here like this. And they are going around in a circle. Now, there's a couple forces acting on the person creating the angle. At 35 degrees, it says 35 degrees from the vertical, so that would be out here. Now, there's basically two forces acting on the person. The simplest force by far is gravity, and of course, gravity goes straight down. And then we've got our circular or centripetal force going off to the side in order to create the angle. So there's two forces, the Fg going down and Fc going sideways. Those two forces put together are creating that 35-degree triangle. So let's sort of map things out a little bit here. We got the two main forces. We've got our Fg going in it's in the vertical direction. Just going down. And we've got the Fc, and that's of course in the sideways direction. And those two put together are creating the angle. They're creating that triangle. So the thing is, we've got two forces creating a triangle. So they are connected with that angle. And if we look at what sides of the little right triangle they're creating, they are the adjacent and the opposite, which means we can apply tan theta to it. So those two forces are creating the angle. And since they're creating the angle, we can apply tan theta to it. Oops, wrong tool. And tan theta of that little 35 degrees would be the opposite divided by the adjacent. Of course, the opposite is the Fc, and the adjacent is the Fg. So if we just substitute our basic expressions in for these basic quantities, Fc of course is mv squared over r, and Fg of course is just mg. And as soon as we do that, we can see that the masses actually cancel out. And that's why everybody ends up at the same angle, same position when they're going around, because the mass doesn't matter. It ends up canceling out in the actual expression. So if we then just sort of put this together, we'll end up with v squared divided by rg, no mass whatsoever. So if we do this, we got tan theta is equal to v squared over rg. We know the angle. V we don't have. We do have the radius and we do have the g. So we can put in our values and we can solve for the v, hopefully not forgetting to square root. So if we do that, v squared would be rg times tan theta. We squared it, and if we punch that all out, should get a v of around 5.4 meters per second. So that's approximately how fast they are going around. Now we can take this, we can connect this back to our basic expression for speed going in a circle. And speed is 2 pi rf. Well, we've got the v value, that's the 5.4. Got the pi, radius was given to you, that's the 4.2 from the beginning. And then we just solve for the frequency. So of course, frequency would be v divided by 2 pi r. 5.4 divided by the 2 pi r, it's actually just the distance around the circle. And we will get a frequency of about 0.20 hertz. Okay, so you could also take the inverse of this to get the period, which would be 5. So 1 divided by 0.2 would be 5. So 5 seconds to go around once, that would be the period. But this is a nice little application of circular motion to a basic, really common fair type ride. And once you start taking like physics, especially circular motion, some energy stuff and whatever, You see this type of stuff everywhere. Things like carnivals and all amusement parks, that type of stuff. It's everywhere. Okay, so there's this nice little simple application. Of course, the key right there is seeing how those forces create that angle, and using a basic trig function to tie those forces together so the masses are able to cancel off. And that's a really common thing. When you have two vectors creating a triangle, use a trig function to tie them together, and often a quantity can often cancel out, and showing that it isn't actually relevant to the situation.